Okay, so welcome to the first sessions. I'm Yosuke Todo, the chair of this session. So this session focuses on the Provable Symmetric Cryptography, and this session has 3 talks. The first talk is combining outputs of random permutations, new constructions, and the tight security bound by Fourier analysis by I.T. Neuer. So please give the talk.
Thank you very much for the introduction. So I will start with some motivation. Okay, so many crypto primitives that we use today are based on pseudo-random functions or PRFs. These include, for example, encryption modes, MAC algorithms, etc. However, in practice, these PRFs are typically implemented by block ciphers, which are pseudo-random permutations or PRPs. And these are secure only up to the birthday bound of roughly Q equals 2 to the power n over 2, where n is the block length and Q is the number of queries. So a classical example for this is counter mode encryption, which works as follows. You have a counter, you apply the block cipher to it with a secret key K, and then you encrypt a message block M1 by XORing it to the output of the block cipher. You get the first ciphertext block, you increment the counter, and you do this process again, and so forth. Okay, so how do we analyze the security of such a construction? Well, let pi be a uniformly chosen permutation. Now we can express the advantage of an adversary and a chosen plaintext attack against this construction, assuming that it makes Q queries using a hybrid argument. And this advantage can be broken down into 2 separate advantages, where the first advantage here basically is a computational advantage, which is the advantage of an adversary in trying to distinguish the block cipher from a truly random permutation. And the second term here is the advantage of an adversary that tries to distinguish the output of a truly random permutation from the output of a truly random function. Now the second term here, the second advantage, this one here, is exactly first of all it's an information theoretic type of problem, and this is exactly the birthday bound, which is roughly Q squared over 2 to the n, and this is because random permutation does not have any collisions. Okay, now how important is this term? Well, if you use a block cipher with a small block length, such as n equals 64, then it's known that actually there are practical attacks against such a construction. However, if you're using AES with n equals 128, this term is typically of less concern. On the other hand, if you're aiming for a high security level, such as 256 bits, then you may still be concerned with this birthday term here. Okay, so the goal of beyond birthday bound security is to design an efficient pseudo-random function using pseudo-random permutations such that the PRF is secure beyond the birthday bound of 2 to the n over 2 queries. And a classical PRF in this domain is called XOP, or XOR of permutations, and it works as follows. So it uses 2 permutations, pi1 and pi2, over n-bit strings. And given a query, which is again an n-bit string, the output of the PRF is defined by XORing together calls to the 2 permutations using the query. Okay? And in terms of security, so last year I presented a paper that analyzed this construction tightly and shows that the advantage of an adversary that makes Q queries to this construction is bounded and actually is roughly equal to Q over 2 to the 1.5n, which is much lower than the Berkeley bound. Another variant of this construction is, I'm going to denote it by SXOP. It's basically a single permutation variant of the previous construction. So how is it defined? It uses only a single permutation, pi, on n-bit strings. And it's defined as follows. So given a query I, which is now an n-1 bit string, the output of XOP is defined by XORing together two domain-separated calls to the single permutation pi. Now, in terms of security analysis, observe the very simple fact that these two calls to pi are different because it is a permutation, and therefore the zero string in this construction can never be output. And this leads to a very simple distinguishing attack with advantage of roughly Q over 2 to the n. And in fact, this attack is essentially the best possible, and this was shown by previous works. Okay, so let's compare XOP with SXOP. And okay, so in terms of security bounds, then we know security bound that is tight for both, but for XXOP it is better. So it is Q over 2 to the 1.5n versus Q over 2 to the n for SXOP, the single permutation variant. On the other hand, XOP requires using two independent permutations, which means in practice the key length is, you actually need to implement it by a block cipher with the two independent keys, meaning that the key length is doubled. Okay, so there seems to be kind of a trade-off between these two constructions. And now the main result of the paper is basically to design a PRF that essentially achieves the best of both worlds. What does this mean? So in particular, we propose a PRF which is called LXOP, and prove its security. Now this PRF uses two calls to only a single permutation as SXOP. On the other hand, the advantage of this PRF is similar to if you were to use two independent permutations. Okay, so this is the main result, and I'll now tell you how LXOP is defined. So it's going to use a function L on n-bit strings, which is a linear orthomorphism. So what does this linear orthomorphism mean? Basically, it needs to satisfy three properties. The first property is that L is linear over F2 to the n. The second property is that L is a permutation. And the third property is that the function defined by x, XOR L of x, is also a permutation. So just a simple example of such a function is the following Feistel-like construction. So you divide the input into two blocks of equal length, n over 2. You exchange them, and then you XOR one to the other. So it's very simple. I mean, it can be implemented very efficiently. So now, how is LXOP defined? Well, so first recall that SXOP was defined by XORing together two domain-separated calls to pi, and now the problem there, kind of what made it relatively weak, is that the zero string could never be output. So now we're going to fix this by post-processing one of the calls to pi by inputting it to L and then XORing the results. Okay, and then with this, we kind of fix this problem, and you can prove that because L is an orthomorphism, then for every query, the output of the LXOP construction is actually completely uniform n-bit string. Now, of course, this is not a security proof because we're only looking at at the marginals on the one marginals here, and we need to kind of consider the distance from uniform on all the Q queries. So it's far from a security proof. On the other hand, it kind of gives you intuition because this attack that worked for SXOP no longer works for LXOP. Okay, so what are, for example, our applications for this PRF? So if we go back to the counter-mode example and replace the block cipher with the LXOP construction and consider the advantage of the adversary, then the birthday term here now becomes much smaller. It is roughly Q over 2 to the 1.5n. Okay, in the paper, we also have additional results. In particular, we prove security for additional PRFs that linearly combine outputs of permutations, but I'm not going to give details here. You can take a look in the paper. So in the rest of the talk, I'll give you a bit of intuition of how about the security proofs. And I'm not going to go into a lot of details because I don't have time. But I'll try to give some, some high-level ideas. So all the bounds are basically proved by Fourier analysis of Boolean functions. And in particular, we develop a framework for analyzing a PRF-F that linearly combines outputs of a single permutation. For example, of such Fs as SXOP, LXOP, and additional constructions that are analyzed in the paper. So in general, the proof has 3 steps. The first step is the following. We're going to bound the advantage of an adversary against F that makes Q queries in the Fourier domain in terms of the Fourier coefficients of the distribution that is output by F. This is a very standard step. In the second step, we're going to reduce the problem to bounding kind of special Fourier coefficients of sampling without replacement distribution, which is a very standard and basic distribution. And then the third step, we're going to apply the framework to analyze these special Fourier coefficients using previously obtained bounds. Okay, so in the remainder of the talk, I'm going to sketch the first 2 steps here. Okay, for SXOP, which is the simplest construction of this type, and most of the technical work is in the third step, and it is found in the paper. Okay, so in the first step, again, we consider SXOP, which is defined by XORing together 2 domain-separated calls to pi, where pi is assumed to be uniform. And denote the output distribution of SXOP, the output distribution function, we're going to denote it by phi. And this is a function from Q n-bit strings onto R. And we're going to denote the uniform distribution function over Q n-bit strings by U. Okay, and then basically a very standard result shows that you can express the advantage of an adversary against the SXOP construction. You can express it by bounding the statistical distance of phi from the uniform distribution, and this is corresponds to this term here. Okay, and the next step is we're going to switch to the Fourier domain. Again, this is very standard. Actually, it's not very particular to SXOP. Okay, so we're going to consider this the output distribution function of SXOP, which is phi, and the Fourier basis. And after we apply some standard manipulation, we get that the advantage of the adversary, or the statistical distance, is bounded by this expression here. So I'm going to tell you what this expression means. So we have a sum, and the sum is over some masks, which I'm going to denote by alpha, which are just qn bit strings. And the terms here are just phi hat of alpha, which is the Fourier coefficient of phi on alpha. So what is this Fourier coefficient? It is basically computed as follows. So we draw a sample from phi, meaning that we draw a sample from the SXOP construction, and then the Fourier coefficient on alpha is the bias of the inner product between alpha and x, where alpha is fixed and x is a random variable. Okay, and the Fourier coefficient of phi on alpha is just the bias of this inner product. Okay, so now let's try to see how do we analyze this expression. Well, let's fix some alpha, which is a qn bit string, and consider a sample drawn from phi. Now recall that SXOP is defined by storing together two domain-separated calls to pi, and therefore this x, the sample from phi, you can express it as y, x, or z, where the string y concatenated with z are just two q elements of f2 to the n sampled uniformly without replacement. Okay, so you can observe this very simple observation. We're going to denote the distribution of output by sampling without replacement by mu. Okay, and therefore plugging this into the bias that we want to compute, we get that x is equal to y, x, or z, and you can express this inner product as an inner product between alpha concatenated with alpha and y concatenated with z. So what I've just, and this bias is, the bias of this inner product is exactly the Fourier coefficient of sampling without replacement on the mask alpha concatenated with alpha. So we have just shown that the Fourier coefficient of phi on alpha is equal to the Fourier coefficient of sampling without replacement on the symmetric mask alpha concatenated with alpha. Okay, now we go back to the expression that we want to bound and just replace this term with the equality that we obtained. Okay, and we get this expression, and essentially the sum here for the SXOP is over Fourier coefficients on symmetric masks of the form alpha concatenated with alpha. Now if you do the similar analysis for LXOP, then the Fourier coefficients you need to consider are of the form alpha concatenated with LT of alpha, where LT of alpha just applies the transpose of the linear automorphism L to each of the Q elements of alpha. Okay, so we need to analyze these structured sums here. Now, previous work showed how to bound such sums over all masks, but here we need to analyze sums which are very structured and are very sparse, over very sparse subsets of masks. And basically, the framework that we devised in the paper shows how to bound such sparse sums using previous work, actually. Okay, now let me conclude. So in this work, we proposed the LXOP construction, PRF, and proved its security. This PRF uses two calls to only a single permutation, but on the other hand, it achieves advantage as if you were to use two independent permutations. Okay, all our proofs are used Fourier analysis, and we also in the paper we show how to apply the framework to additional related constructions. And in the future, I think it would be interesting to extend the framework and to apply it to additional similar constructions. That's it. Thank you.
Thank you very much. Okay, so the time is limited. So if someone has a quick question, so please come to the microphone.
Just a quick question. When you look at the space of all the possible formulas which contain 2 calls to pi, you are using the L on the outputs. You could use L's on inputs. For example, you take pi, you don't use domain separation, but you call pi with x and you call pi with L of x or something like this. Have you considered this kind of things where L is used both on the input and on the output?
I think people have considered it. So I don't think this would give you something better in this case. My feeling is that you would get roughly, I mean, at best you would get the same, yeah.
With the 1.5
Yeah. Yeah.
Thanks.
Okay, thanks a lot. Thanks again. Okay, so the second talk is the impact of reversibility of parallel pebbling. Blake Holman gives the talk. Please, if you need, please use it.
Okay, thank you. I'm going to be talking about the parallel reversible pebbling game and how we can use it for quantum attacks on memory hard functions. So a common problem is that people's hashed passwords get leaked, and then brute force attackers use specialized hardware like ASICs to recover the hashed passwords. Memory hard functions protect these passwords from brute force attacks. Well, how do we do this? Well, the idea is that we want the computation costs for hashing the password to be dominated by memory costs. The goal is that we want the attacker to lock up a large amount of memory for the duration of the computation, because even though the time cost for the attacker is relatively small, the memory cost tends to be uniform between the different hardwares. So there's a few ways that people tend to measure cost with memory hard functions, but the standard approach is to use something called cumulative complexity. And that's just the sum of the space usage over time, or equivalently, the average space usage times time. So if you have an algorithm and you plot the space usage over time, then cumulative complexity is just the area under the curve. The idea is that the higher our cumulative complexity of our memory hard function, the lower advantage that an attacker with specialized hardware has. Okay, so what is a memory hard function? Well, it's defined by 2 things. One, a graph that encodes data dependencies, and a hash function. Each node has a label. Given the input to our function, the label for the first node is the hash of the input. The label for all the other nodes is just the hash of the labels of their parents. So the label for node 3, for example, is just the hash of the labels 1 and 2. Lastly, the output of our function is just the label of the sync node in the graph. Okay. So the primary way we analyze memory hard functions is via pebbling games. So pebbles here represent chunks of available memory. Placing a pebble on a node represents computing the label for the node and then storing it in memory. Likewise, removing a pebble represents unallocating that memory. Okay, so let's go through a quick example. If we want to pebble this graph, we can place a pebble on node 1. Oh, sorry. There's a couple. So the game is played in rounds, and the first rule is that we can only place a pebble on a node whose parents are already pebbled, which corresponds to computing the labels. And then we can always remove pebbles from the graph because we can always unallocate memory. So to start pebbling this graph, we can place a pebble on node 1. Now we can place a pebble on node 2. And now that we have pebbles on node 1 and 2, we can pebble node 3. Now we can remove the pebble node 1 to free up some memory, and finally we can pebble the sync node, which corresponds to computing the memory hard function. Okay. So we talked about that we want to deal with quantum attacks on memory hard functions. And so the idea is that a quantum attacker might be able to implement the memory hard function and apply standard techniques like over search to get a quadratic speedup, maybe searching over the dictionaries to crack the passwords. Now, to do that, you usually need to implement the memory hard function as a quantum circuit. And this is, we need to be able to evaluate the function in superposition. In other words, we need a coherent quantum circuit for it. The problem is that this can be much more costly than just evaluating it classically. And that's because the quantum circuit is reversible. So a natural question is whether or not we can use these classical pebbling techniques to analyze the cost of these coherent quantum circuits. Well, let's see where this might go wrong. For example, consider a very easy memory hard function, which is just a hash function applied on itself n times, represented by a line graph. Well, a classical machine can just compute the function in place really easily. So we have our input x. We can compute h of x, h of x, and so on until we get to the end. And then you can see the corresponding pebbling for this evaluation strategy. So that was really easy. But what about if we have we want to build a quantum circuit for the memory hard function? Well, then it gets a little bit more tricky because we can't just compute it in place. That's not reversible. Generally, what we would do, the standard technique is to take x and then to XOR h of x into the next register, and then again, and so on until we get to the end of the computation. And again, we have a pebbling representing this kind of computation. So now we're left with a dilemma. We have all of this garbage left in our registers, and so the natural technique is just to uncompute it reversibly by applying more queries. So we can query h2 of x to get h3 of x again, cancel out that register, and so on until we finally get to the correct configuration where we took our input and then we finally got the memory hard function output in our register. So this reversibility implies additional constraints on our pebbling scheme. And with these new restrictions, we get the parallel reversible pebbling game. Okay, but we've encountered a bit of a problem because the classical algorithm for this memory hard function had used constant space and n time, whereas this quantum algorithm we've talked about uses linear space and linear time. So while the cumulative complexity of the classical algorithm is linear, the cumulative complexity of the quantum one is quadratic. And so we really want to find out whether this overhead in cumulative complexity is necessary. Okay, so this is our question, and we can rephrase it in a slightly different way. We know that this classical pebbling game is easier than the reversible one, so maybe we can try to show that for any classical pebbling, there's a really close reversible pebbling to it. And this is nice because for classical pebbling, we have lots of resources. They've been used to analyze memory hard functions for a very long time. Whereas reversible pebblings are relatively new. There's not many techniques. Again, the problem is that with the classical pebbling, we saw that it doesn't really represent coherent computation, whereas reversible pebblings can be directly compiled into quantum circuits. And so that's what we do. We provide a cumulative complexity preserving map from irreversible classical pebblings to reversible ones with a sub-polynomial overhead and the time complexity. For memory hard functions, This means that we can take our well-known classical attack and then use reversible pebbling to turn it into a coherent quantum attack without blowing up the cumulative complexity like we saw in our example. So these are what we're going to talk about today, but we have some other results in the paper. We show that you can't do too much better than this by proving a separation for the classical and reversible cumulative complexity of the line graph. We also give some tighter bounds instead of this generic transformation for certain memory hard functions. Okay, so let's go over how we map classical pebblings to reversible ones and take some pebbling P from our original graph G. And we want to map it to a reversible pebbling while maintaining cumulative complexity, which again is the average space usage times time. Okay, the idea is that we can take our pebbling, the classical one for the original graph, and actually treat it like a new memory hard function. In this case, a line graph. Here, we're again viewing the pebbling as an iterative function, but this time the function maps the pebbling configuration 1 to the pebbling configuration 2, and so on. And in this way, we can pebble this new line graph, and placing a pebble represents storing the pebbles from the configuration of the classical pebbling, and likewise removing it represents removing those pebbles as well. So, what's the point? Well, it turns out if you have a reversible pebbling of the line graph, then the line graph that represents the classical pebbling of G, then it corresponds to a reversible pebbling of G. In particular, this kind of transformation does preserve the time complexity of the line graph pebbling, and then the space complexity just has a multiplicative overhead in the space complexity of our line graph pebbling. And so what we do is we combine this result with a prior result, which is just a linear time subpolynomial space line graph pebbling to get our reversible pebbling of the original graph. And the result is time complexity, linear time complexity, and just a subpolynomial overhead in the space complexity. Okay, so this is very cool, except it doesn't solve our problem, right? Because we're trying to preserve cumulative complexity, which has to do with average space usage, but the average space usage could be much less than the maximum space usage. In particular, you can imagine that our pebbling at some time step t1 has a lot of pebbles on the graph, but in general, there's not very many. If our line graph pebbling keeps a pebble on node p sub t1 for a long time, then we're going to blow up our average space usage. Okay, so how do we tackle this problem? Well, it's actually not, we can actually still use our result from the last slide, meaning we can take a reversible line graph pebbling and do the transformation to get a reversible pebbling of G. But the key is we're going to instead make our pebbling take into account the size of the pebbling configurations of our classical pebbling. Okay, so like before, we have the line graph, and each node represents, like node 1 represents P1, the pebbles that the classical pebbling had on time 1. The weight of a node is going to be the number of pebbles in that configuration. And what we'll do is we'll classify the nodes as light, medium, or heavy. The idea is we want to pebble this graph, and this time our space usage is going to be defined by the sum of the weights of these nodes. And what we want to do is pebble this new graph with low cumulative complexity. Okay? So what we do is we imagine that we only want to pebble these easy light nodes, And we apply our pebbling strategy from the previous slide to this subgraph. And then we'll see that we have to fix all of the illegal moves in between. Okay, let's go through an example. So to start out, we can place a pebble on node 1. So now we want to place a pebble on node 6. But we can't really do that, so why don't we just call our algorithm again recursively and pebble this line graph. So we can place a pebble on node 2. But then, there are some heavier nodes in between, so we have to pebble those. Okay, now that we've pebbled the heavier nodes, we can pebble node 5. But remember, we can't keep pebbles on the heavy nodes for too long, or else our average space usage is going to blow up. So we're going to quickly unpebble them, okay, to place a pebble on node 6. But now we have pebbles on the medium nodes, and we don't want to keep those around for too long either. So we're going to, again, unpebble node 5 and 2. So we're going to have to repebble the heavier nodes 3 and 4, remove a pebble on node 5, unpebble, remove it on node 2. And finally, we can remove the pebble on node 1. Lastly, to pebble node 8, we just have to pebble node 7, and unpebble, and now we can finally finish the pebbling and compute the memory hard function. Okay, so what did we do? Well, it turns out that this strategy preserves cumulative complexity. So whatever the cumulative complexity of the original classical pebbling was, the cumulative complexity of this reversible one only has a multiplicative subpolynomial overhead in the time complexity of the original pebbling. Okay, so to wrap up, we gave a cumulative complexity preserving mapping from irreversible pebblings to reversible ones, and that implies quantum attacks on memory hard functions. There are a couple open problems. First is whether or not these reversible pebbling bounds hold in the quantum random oracle model. And lastly, if there are any applications of low CC quantum circuits to other cryptographic problems. Okay, thank you.
Thanks a lot. So if you have a question, please go to the microphone.
So you are introducing quantum algorithms which only give you trouble by requiring reversibility. But they might also give you advantages. For example, your pebbles might be superpositions of pebbles. I'm not sure whether it is possible to do it. Maybe it's possible to do it for certain kinds of transition functions and not for others. But has anyone considered the positive side of using quantum algorithms in the pebbling game?
So I think I understand your question. So this is not, I think you're asking, you could possibly use a quantum algorithm to compute a memory hard function classically faster. And that's an interesting question, and yeah, I don't think that's been explored yet. This pebbling game is specifically for kind of taking a classical algorithm and making it callable in superposition.
But it could be a much faster pebbling if you are using pebbles which are simultaneously at multiple locations in some kind of superposition, right?
Yes, that's possible, but yeah, not for, we do not cover that in our work.
Thanks.
So if I understood correctly, the basis of the problem is that you cannot compute in place the hash function for quantum circuits. But given that quantum circuits are reversible, you could just output on the same memory block the hash and the ancillars, then it becomes reversible again.
Yeah, I don't think I quite heard all of it, but so the reason we can't compute it in place is because you would only be able to do that if instead of a hash function you had a permutation, because otherwise it is not reversible. And so yeah, you always have to to make it reversible, you have to add extra space so that it can become unitary.
But the circuits which compute the hash itself is reversible. So even if the output itself is not reversible, if you add the ancillas of the quantum circuits, then the sum of the hash and the ancillas is enough information to uncompute the circuits and be reversible.
I see, but I think you're still talking about adding like more qubits to make it reversible.
Not really.
Oh,
Maybe
sorry.
we can talk about it later.
Yeah, my bad.
Okay, so thanks a lot. Please go to the next talk. The final talk of this session. Okay, random oracle combiner, Mark Rudanga's style. And Peter Hall gives a talk. Okay, so let's start.
All right. Thank you all. I'm going to present this work on random oracle combiners, specifically Merkle-Damgard style, and this is joint work with my wonderful co-authors, Eli Golden and Yevgeny Dodis. So what is a hash combiner? What do we want to do? Well, suppose you have the following situation where you have some company or something that has their own super cool new hash function that they want to use for some application. And they go to whatever, local government or whatever, and they say, okay, can we use this for our application? And maybe this regulation body says that, we want you to use SHA-3 for it. The company really wants to use theirs, but we want to make sure that both parties are happy here. So this is where a combiner can help us in that, the combiner can take in both of these hash functions and output some sort of new hash function that's this C SHA-3 super hash, and this will hopefully have whatever desirable properties that both of them want from it. Specifically here, we're interested in preserving properties of security from the inputs kind of being expressed in the outputs. For this talk, we're also going to be talking about structured hash functions in the sense that rather than a monolithic hash function that just takes an input m and outputs the hash of that m, we consider kind of like a Merkle-Damgard transform on some underlying compression function. So for the Merkle-Damgard transform, we take our message m, we cut it up into these blocks here, and what we're going to do is we're going to piece by piece evaluate this underlying compression function on those blocks. So we start out with M1, we circuit the output of that hash to the next stage, which takes in M2 additionally, and so on and so forth, until we get to our final block, which we can then output as our overall hash. The advantage of Merkle-Damgard hashes is that the underlying hash, this capital H here, can be much less compressing than the overall hash compression. And so we might get better practical effects because of that. So before we talk about our results, I want to talk about some background. Namely, with respect to hash combiners, we have some sort of barrier as seen here. So namely, this is that a combiner, one valid combiner for collision resistance is that you just concatenate the two input hashes. And what we see is that as long as one of H and G is collision resistant, then this overall CHG will be collision resistant as well. A similar construction works for one-wayness, and there are other constructions for pseudorandomness, max, and so on. Now, Pierre Zak in 2007 showed that length doubling, as this one is essentially optimal for collision resistance. Now, Mittelbach in 2013 gave some evidence to the contrary of this, where the caveat is that instead of assuming that one of the inputs is only collision resistant, you actually assume that one of them is a random oracle. In a prior work, my co-authors and I, as well as Ferguson and Pierre Zach, introduced the notion of a random oracle combiner, which extends this idea of the Cryptophia short combiner. Namely, what our concept there was that if one of the input hashes is a random oracle, then the combiner, C, is essentially this big random oracle overall. How do we do this? Well, we use the indifferentiability framework for this. So namely, we say that any efficient distinguisher cannot distinguish between interacting with a random oracle, this little h, and our actual combiner, our actual construction, versus interacting with this random oracle big H, which is what our combiner is, as well as some sort of simulator simulating this little h now. And so this is what it looks like here, and essentially we want indistinguishability between these two. So given this, applied to our setting, we see that what we will do is suppose that one of the two inputs, R or G, is a random oracle, and we give the other one query access to this random oracle. So G is fairly strong here. What we want is that this capital C here is indifferentiable from a big random oracle. And now, given this, in our ideal world, we are going to, instead of having little h be a random oracle, we now have it be a simulator, given that we have this random oracle as our combiner. Now, as a note here, our prior work showed that actually this sort of notion of a random oracle combiner actually requires some extra input randomness for the combiner. What we will do is that we will also give the simulator this salt. Now, this previous work gave a basically optimal construction for hashes with good compression. That is, instead of concatenating them, you can just XOR them. The downside is that for various applications, this doesn't give evidence for when H and or G are Merkle-Damgard. Namely, the issue here is that although we have the fact that our construction is indifferentiable from a random oracle, and though we have the fact that a Merkle-Damgard transform of a hash function is indifferentiable from a random oracle, the composition of these two only works when both of them are single-stage games. Unfortunately, our random oracle game is two-stage. Namely, you first output your adversarial hash G, and then you're given the salts and you want to find a collision or find some sort of distinguishing. So what we need for our situation to get this more practical application is we need for a given combiner to work with the Merkle-Damgard separately. So that is, we're going to assume now that one of H or G is only a random oracle of like some fairly mild compression, and our combiner is only going to call H star and G star, where H star and G star are the Merkle-Damgard transforms of H and G respectively. So this will support very long input messages, but we still need our message output to be less than 2 times the length of H star or G star. So what are our results for this? Well, we see that a very similar construction to as before works, where the only change here is that now we replace H with H star and G with G star. For some parameters to understand about this, whereas before we had that our individual hash and our overall hash compression must have the same compression, some sort of n plus delta to n. We now get that for an individual compression of n plus delta, we get essentially delta times L overall compression, where L is however many times we run this Merkle-Damgard transform. Now, a caveat here is that the length of our salts, both in the original setting and in our new one, must be the size of our message space or the size of each individual message plus security parameter extra. This exists in the previous, and we actually will have this here as well. Before we get into how we prove that this is a random oracle combiner, we need to first kind of talk about why our previous techniques don't actually extend to this setting. So what fails in our previous proof for the Merkle-Damgard setting? Well, in the monolithic setting, we critically used the fact that our salt was longer than our input messages, and by doing this, we could show that G of M prime Z2, so whatever this adversarial hash computes, cannot actually compute H of M Z1 for any complete message M and complete Z1. Now, what does this rely on? This essentially relies on the fact that our salt Z1 is larger than our message M prime or M. And so we get that we cannot store all of it, or we cannot compute on all of it in G, and this does the job for us. So given this, why is this important? Well, if you have this, then your simulator can actually answer complete H queries without worrying about any sort of recursion. Namely that this G of M prime Z2 does not call some H of M Z1 somewhere else that we weren't ready for. Unfortunately for Merkle-Damgard, it's actually pretty easy to construct a pair of messages and define our adversarial hash GH such that the Merkle-Damgard on G, on M prime Z2, can compute completions for H star of MZ1. So namely, what does this attack look like? Well, let's consider H to be halving of its inputs. Our message M prime that we're going to feed to G2 then is just going to be this H star of MZ1 block 1 all the way up to block K minus 1, and then on the end also append this final block Z1K. So these are just Z1, this Z11, Z12, and so on are just length n blocks of our salt Z1. Well then, we can define GH pretty easily so that GH star of M prime Z2 actually computes exactly this H of M prime, which applying this H of M prime we see is actually the completion of H star M Z1. How will this GH work? Essentially, if your input block is 0, you compute H on your inputs, and otherwise do nothing. So what is our lesson here? Our lesson is that intuitions for the monolithic case may not carry over to the Merkle-Damgard setting. So as for what proof we do need, well, as before, we want to build a simulator such that sim star of MZ1 plus G star of MZ2 is equal to H of M, so that our distinguisher cannot distinguish between the real setting, where this is the case, and our ideal setting. Sim has to answer all queries at random to look like little h, but it must also satisfy this above equality here. So we need to spot all of these constraints. We need the last value of h to be free in some sense. And then finally, what we will see is the most important one is that we actually need the runtime of the simulator to be bounded. Why is this a concern for us? Well, looking at how our simulator will work, essentially what we will do is we'll just have this large table here where we record down every time we have a new input here, and we will record what our output is, which we will just generate by sampling. What this will allow us to do is easily check what the length of an overall message is by just checking when the output of one stage, R1, is equal to the first input of another stage. And so this will actually let us easily get with our second input B here, what essentially the chain of message we will be building up to. Now, unfortunately, when we get to a stage where we might complete some sim star of MZ1, we will need to now check that we actually satisfy, we'll check that we actually output and satisfy this h of m plus g star of mz2. And so what we'll need to do for that is we will need to actually compute this g star within the simulator. So, okay, g star and each individual g can call sim potentially quite a few times. And so we need to fill in those queries too so that we're consistent later on. Well, this might introduce that we also get something that's of length L plus K and something that ends in Z1. And so we might need to recurse again on some now new G star input. And we might need to do this again and again. And so the worry here is that we need to make sure that we don't infinitely or even just, overwhelmingly recurse. So we cannot argue that that G never queries H on some completion. So what we're instead going to do is claim that for D to find a message such that G completes an H star query, then D must have queried H star of M prime itself. So it must have gotten a good portion of the way there. So if this is true, then the number of queries made by recursive G calls is just upper bounded by the number of calls that D makes. And because we know that D is bounded, then we've bounded our recursion. So in order to argue this termination, what we're going to do is we're going to map out kind of what D might do on this second stage. So note that we only care about queries that end in Z1 and are length L plus K. Why is this all that we care about? Well, because for anything else, we're going to randomly sample. So we need to bound how many queries reach there. And in order to do so, we're just going to consider, okay, well, Z1 or D will start querying some sim queries, and maybe it'll keep querying until it gets all the way to the end, essentially computing some sim star on some message. At this stage, well, we'll have to start doing our recursion, and maybe this orange will start building up this way, our recursive call. Our first property here that we need is that a blue query cannot follow an orange query. Why is this the case? Well, essentially a blue query, we could query without first querying those orange ones. And in essence, this will let us predict random oracle outputs. Essentially, this recursion will predict its output to the blue. Later on, maybe we have a similar situation where now we want to make sure that a green query cannot follow an orange query, where a green query was generated by the second blue one. This will essentially follow the same argument as before, but now instead of D predicting the random oracle output, sim will. Finally, our last query here is that an orange, or our last property here is that an orange query, a series of orange queries, can't find all of Z1 on its own. Why is this the case? Well, it essentially comes from the fact that Z1 is longer than the message, and so this singular chain of orange queries can't possibly hold all of Z1 in it. This is a similar argument to how we kind of described before in the previous work. Given these three properties, we see that orange queries can only complete blue paths, essentially triggering a new recursion, for the blue paths that already extend past this length L here, and so are already in the Z1 stage. And what this means is that in order for us to have any additional recursion, we must have already directly queried past length L, thereby bounding our recursion depth. So this is, again, the hard part about showing termination, and this will actually help us a good portion of the way to our random oracle combiner proof. So as for some conclusions, we expand in this work the practical utility of random oracle combiners by constructing them for Merkle-Damgard-based constructions, as opposed to the monolithic case which we looked at last time. And we only rely on the underlying compression function to be a random oracle to get this argument. Some open questions I will mention as well. First of all, we want to know if we can construct a random oracle combiner with very small salts. So we looked at the size of the salt being the length of the message plus some security parameter. We have no concrete evidence that it can't be as low as just the O of the security parameter. And in addition to this, we want some constant number of calls. Alternatively, we could have an impossibility result in this domain. And so that is all my time. So thank you very much, and feel free to look at the paper here.
Okay, thank you very much. Do you